All right. Hello, everyone. Glad you're all here. I'm going to be talking today. My name is Stephen Newby. I'm going to be talking today about memory management, specifically in C, but it's actually a topic that you should really know no matter what language you're in, no matter what framework you're in. It surprisingly comes up out of nowhere so often. Your data lives in multiple locations. It's stored in the hard drive whenever it's installed and set up. Whenever the program's run, it's going to be loaded into RAM, the CPU. In some language like Python, JavaScript, you're going to have some. A lot of the memory management is done automatically, but with each one of those, they manage the memory very interestingly and oddly. In language like C, like what you guys were learning today, it's all up to the programmer. You guys are manually choosing what to do all the time, making all the decisions, and you have to keep track of a lot. So it's a bit of an involved situation, but it gives you so much fine control that the performance of your code can be so much better than if you had written it in a language that does automatic memory management. Whenever you think of, I was trying to think of a good analogy to be thinking about how everything's done, and I settled on a library, at least to start out. You can think of like programs being stored on bookshelves. Whenever you choose to run a program, it's like you ask a librarian to bring several books to you to like your desk area, like within like a reading room. And there are many different ways that data is used and set up by the computer, but the two main areas that we're going to mainly be focusing on today is the stack and the heap. And you can think of those as, you can think of it having like a nice little rectangular area, like directly right next to you where you write notes. And this little area, you write notes on about an author, then you put another sheet on top of it, write notes about a book, put another sheet on top of it, write notes about a chapter, put another sheet on it, write notes about a paper, about a specific page. And that, what I would see is a stack. It is where things are just nicely stacked up vertically. A different place to store memory is the heap, which kind of goes off of what it is called. It's more like a pile, a little bit further out of reach, and it's kind of a mess. There's a lot involved there, and you have to know exactly where something is, like, in order to access it and use it. The stack itself is founded on the principles of last in, first out. This prioritizes like the most recent function or like the most recent page of notes is accessible to you at any moment. And it has a lot of information like the location to where the previous page was, the location of the calling function, its own data, parameters passed to it, etc. The stack is, I like to think of it like an OCD's person, like stack of notes, where it's just like there's an incredible amount of detail, attention to detail, where everything's just like highly decorated, highlights and how everything connects to each other. When you're dealing with stack frames, specifically, the stack is made up of stack frames. It's not just like the code that you're running. It's all the information that each function has access to, including the instructions of how it works, what was passed to it, etc. And this is what is stacked on top. And so whenever you call a function, the previous function is kind of no longer in focus. The information is no longer accessible, and the CPU is solely focused on the current function that you're in. So if you have so it cannot see anything that wasn't passed to it. It just has its own information, what was passed to it, etc. And yeah, these just stack up, and as soon as you use it, if a function is done, it dissipates, it's over, it's no longer accessible. The data is actually still written in memory, which is like a security risk thing if you don't manage it right. It's a nice little thing that can pop up at the worst moments. All right, let's think about a simple addition problem, addition program. There's a main function. It calls a function to add some numbers and print them. Whenever you call the main function, the main stack frame is going to have this type of information, like whatever called main. So whatever called main is generally like the it's part of the CPU whenever you call main. And you get your variables set up and all the instructions involved. And then whenever you call print add, the information in, like this is no longer, I just want to make sure this is visible. Like this area is no longer like accessible. So this is the only area that is currently functional. And it deals with this specific information. And whenever you call a printf itself is a function as well. So whenever printf is called, it has its own information, its own way of doing things. And later in the semester, you guys will be writing your own printf, which is a ton of fun. Actually, it's a good time. You deal with a string, you deal with a bunch of arguments you have to parse, variadic functions, etc. It's a lot of good time. And whenever the printf is done, disappears. Whenever the print add's done, disappears. And whenever the program's over, main disappears. And this is generally how things work. You go back and forth, things are called as needed, and then the stack frames will go out of play. A weakness of the stack, this is something Ryan talked about earlier today, is that it cannot handle anything of a large size. Generally, the stack is something set up for only a very small amount of memory initially. You can write programs in a certain way till you can preset how much memory you want the stack to have. But generally, you're only granted so much information, so much size for it. The heap, which we'll talk about in a moment, is nice, but then it's effectively the rest of your RAM, to be honest, which is pretty good. Right. So the things that go into the stack, the things that make it so fast, is that information that goes into it is information that's known at compile time. So if you have in your code A equals 5, then the CPU's like, okay, I understand. The compiler's like, hey, I understand that you have a variable called A, and that it's initialized to 5. Excellent. I'm gonna preset that up, and it's gonna be ready very quickly the moment you launch this function, this program, which is great. It's nice it produces speed. It allows things to run very quickly, very smoothly. But if it's something where you don't know the actual size of it or you don't know the value of it, especially if you don't know the size of it, the compiler is not going to place it in the stack. So it needs to be set up elsewhere. Another issue with the stack is that scope is an issue. Whenever you're done with a function, whenever you create any variable that's created in the function is no longer accessible after you get out of it. So that's the nice thing about the heap, is that you can actually create variables that persist throughout the lifetime of the program. That's the nice part about it. There are limitations and issues for it. Anyway, yep. All right. The heap. Probably shouldn't be standing in front of the words you guys are supposed to be reading, actually, now that I think about it. It's all good. The heap. You can think of it as like a giant pile of notes. You can also think of it as like having a dynamic storage warehouse where there are tens of thousands of bins where individual items are stored. It's a large place where anything can be stored, but it's a warehouse. Things move slowly. It takes longer to reach them, to store them, etc. I was reading like there are estimations between it's 5 to 100 times slower to access things in the heap, depending on the structure, where it is, how segmented it is. So if you're in a very performance-intensive program, try to put as much on the stack as possible. Right. So whenever you're using the heap, it requires you to actually request space from the CPU to get it allocated. So if you have like a complete set of Mark Twain, like if you have like 10 complete sets of Mark Twain in the warehouse, then you need to request 10 times the size of each set of books. The warehouse will contain its contents, and it'll keep that reserved space until you tell it that you no longer need it. The request, as you guys learned today, was a function called malloc. It's a memory allocation function, and you just say, "Hey, this is the amount of size I need for this variable, for this data type," and it'll reserve it for you, and it'll stay open. And one thing that malloc does, and calloc and realloc do, is that, I think realloc as well, they all return a pointer to the location in memory where the allocated memory has been allocated. The pointer is something you have to keep a strong track of at all times, understanding where exactly your information was stored. Because if you lose it, it's still being stored somewhere, and your data's gone, or you now have an inefficient usage of memory. I was curious, where do you guys think a string is stored? Stack, okay. Any string. Okay. All right. It's a little bit of a trick question, actually. Whenever the value of the string, whenever the contents of a string isn't known at compile time, like if you're going to run a program that asks a user to enter in their username, whenever you do that, then the computer is going to have to store that on the heap, because it doesn't know at the time of compilation the size of a string, because a string doesn't have an actual size. Like there's no standard size of a string. You can create an array of characters and have it like a buffer basically, and have a preset size. And that's generally what you do in C whenever you're trying to read in information. But if you're trying to store it as a string itself, like as a char star, then that is going to be something that is that itself is going to be stored on the heap itself. Yeah. Now, if you do know what the contents of the string are at compilation, like if it's like the name of the program that's going to appear whenever you start it, that's actually stored in a different location, not the stack and not the heap either. There's actually quite a bit involved. There are multiple different locations for every single process. There's a data section, there's a read-only data section, there are like 5 other sections just for like Linux versions of programs. It's an ELF format system. It's kind of involved, but anyway, whenever you create a string, it's stored in the data section, which is also similar to the stack, but it's more persistent. It's persistent like the heap, but it's in a nicely quick accessible location like the stack. All right, it's always good to give back to your community, and whenever you want to, you're going to definitely need to be keeping track of when your information is no longer necessary to be held. You're going to need to be able to, yeah. There's a complexity in programs arises real quickly. Whenever there are multiple ways for a program to exit, you have to keep track of which variables have been allocated at the time of that exit, and it presents itself a very involved problem that you guys will have fun writing. It's a good challenge, to be honest. So use free to do so. It's crucial to do to free everything. And it's simple. You use free and you put the name of the variable. And it frees everything that's in the location. Yep. So, right. A very quick comparison I was talking about earlier. Optimizing the performance of your program requires knowing when to use a stack or when to use the heap. The stack is fast. The heap allows for things to be accessible at all times, basically, but you just have to keep track of it. Yeah, and it's just, but the heap's a lot slower. So. Right. So you're asking whether I'm trying to understand. You're asking. Could you repeat that?
So like there's a program running, right? And it's like you have the program running, but data has to be managed. So like kind of like cache memory is like having like a hash or like on a low level, having like more cache memory that's accessible for the program that's running versus like data being like, okay, this is the data being used on the market. You know what I mean?
All right. All right. So yeah, the data would be.
If you're pulling data from a source,
Yeah.
because we don't know the size of that data, it's probably going to be allocated. So stuff we allocate on the stack the compiler needs to know ahead of time how the size is. Whereas if we're allocating on a heap, we can go grab whatever we need whenever we need.
Yeah. Yep. So yeah, So yeah, if it's being pulled in from an external location, you can use a buffer to read it in, as long as you know the general size of it. You can use a buffer as to read it in, and you can read that into the stack, kind of. You can read that into the stack variable like as a buffer. If you don't know the size of it though, like if it's something that's going to require multiple buffer reads, then that's probably going to be allocated to the heap. Yeah, a lot of this is just like making sure the computer knows the size of something. If the computer doesn't know the size of it, it's going to be in the heap. Is a general good rule of thumb. Yeah.
Also, if you do know the size of it, but it's massive, there's then you risk overflowing the stack. Because the stack dictates the size. Whereas the heap is essentially the rest of a memory.
Yep. All right. Yep. All right. A few quick common memory errors. Every program has memory leaks, especially if it's complex. And apparently even like Linux, like ls functions or whatever, also have. Yeah, they're like they're micro, little, tiny little things, but.
I mean, I guess the general idea of like LS is that program is so short-lived, it doesn't need to be optimized.
Yeah.
Because once the program stops running, all that memory is gone. They're not, it's no longer yours.
Yep. Yeah. So memory leaks do occur. You can definitely notice them when your programs like they run a long time and then they just get slower and slower and slower. That's generally a good sign of a memory leak. That is something that you guys will have to be in charge of, and there will be so many different ways for things to leak. So it's a good time. Tools like Valgrind are very useful, especially if you start learning all the flags to use with Valgrind and how you compiled it. Then you can create it. You can make it so it's very debuggable, and it's much more quick to, get back on your feet and be programming. Dangling pointers is a thing whenever you got something that's been freed already, but then you start, you try to use the variable again, and the variable still is pointed at the location that it was assigned, but that information, like the CPU may have written over already by another process, so you could be reading in information that is of the wrong data type to be expected, or of course just the wrong information. It's also an issue that can be exploited by hackers to find out other information that's being stored by the program, including how the program runs and sensitive content like user passwords, etc. All right. Modern garbage collection software. So modern languages have automatic memory management where they do their own like garbage collection. Basically, it's where they do their own allocating and freeing for you. This can be pretty great in that you just care less so much about it. And even those languages, like the heap is less far away, so it performs generally a little bit faster than the heap it does for like a language like C. However, the issue is that it can cause its own issues. There are multiple trade-offs you get for it. Garbage collectors require maintaining overhead. Like they are an actual process that is running in the background. They're monitoring things. There's a performance. You're going to get a performance hit to your program from it running. And one thing that's really frustrating is that the way they often run is that they fully stop your process, like the processes of your entire program, to do their memory management, to do the memory management cycle. So you're going to get latency blips from time to time. If you start wondering like why on earth I get these random latency blips whenever I'm running this program, and it's a massive program with a lot of things that were allocated effectively to the heap, it is possibly because of the garbage collector activating. You can try to optimize your own garbage collector. There are specific libraries that are out there for having more optimized garbage collectors, but it is an involved process that will take time away from everything else you're doing, so there's a lot of trade-offs to be involved. Languages like JavaScript and Python I don't think they allow any sort of personal customization of their garbage collectors. I'm not certain. So you have to know the strengths and weaknesses of the garbage collector going in and how much it may impact your program. All right, so yeah, why this matters. Performance and reliability. Once you understand this, you get the ability to create like high quality software. It's very useful. So here's the TLDR. Memory is managed in multiple areas, but two main areas that we care about is stack and heap. The stack is fast, automatic. It's last in, first out. But it has a limited size and lifetime. Heap, flexible, dynamic, requires more management to take care of. Use malloc and free to allocate and deallocate. You must free what you malloc. Forgetting the free causes memory leaks. And using memory after a free can cause undefined behavior. It's always fun whenever you don't know why something happened. And yep, garbage collection is pretty nice, but it has its trade-offs. All right. Any questions? Yeah. Yeah. All right. Yep. I'm glad. All right. Cool. Bye, guys.